Good evening, one and all. Am I audible? Am I audible? Please give me thumbs up or put a chat in the chat box so I can understand whether I am audible or not. Am I audible? So please give me a reply. Am I audible? Am I audible? Hello? Yes. Good evening once again. Welcome to Goscore Learning. We are the fastest growing EdTech in GCC. Our aim is to provide education for all. Educational democracy. Okay, welcome back again. So my name is Rahul Raj. I am from Department of Physics, Goscore Learning Middle East. So today we are discussing the fifth chapter of grade 12 physics, magnetism and matter. So we have already completed the fourth chapter, moving charges and magnetism already. So those who have any doubts in the fourth chapter, please do visit our official YouTube channel, and you can see the four part of the moving charges and magnetism we have discussed in detail, as well as some previous year questions, neat exam questions. So far we have discussed in that classes. Okay, so today we are moving to the fifth chapter, magnetism and matter. And for dear students, there are some happy things that is happening in this chapter. Why? Because we are dealing only most of the equations are we are dealing with in this chapter is qualitative treatment only, which means there will be no derivations, only equations are to be by hearted like that. Okay, so this chapter have very resemblance with the first chapter of grade 12 physics, that is electric charges. So in the first chapter, electric charges and field. So here it is magnetism and matter. So in the first chapter we deals with electric field, electric dipole and electric field due to a dipole. So in this chapter, if you see, means you can see this topic, magnetic field lines. In the first chapter we have deal with electric field lines. So there is a resemblance with magnetic field lines in the chapter. Okay, so magnetic field intensity due to a magnetic dipole. So in the first chapter we have seen electric field intensity due to a electric dipole. Due to an electric dipole we have discussed in the first chapter. So for an electric dipole we have discussed, or we have derived expression for electric dipole on an axial point, expression for electric field due to an electric dipole on its axial point, as well as on an equatorial point. So same thing happening here. So we'll be dealing two equations for magnetic dipole and torque on a magnetic dipole in uniform magnetic field. So we'll be discussing that too. So we have discussed torque on an electric dipole based in magnetic field. We have already discussed. So here we'll be discussing torque on a magnetic dipole in a uniform magnetic field. So there is a resemblance. So in the equation also you can see the same resemblance you can see. And here bar magnet as an equivalent solenoid, magnetic properties of material for paramagnetic material, diamagnetic material and ferromagnetic material. These materials are new ones for you. We'll discuss in detail in this chapter. Magnetization of materials we will be discussing, and effect of temperature on magnetic properties. So if you see, means you can see the first three topics have very resemblance with the first chapter of grade 12 physics. So those who are thorough with the first chapter will be feeling comfortable for learning this chapter easy. Okay, so we can handle this chapter very much easily once you learn the chapter 1. Okay, is that ready? Then we can move. Okay, so we can move into the chapter. So please give me thumbs up, then we can move. Okay, so put your comments on the chat box. If there are doubts, you can put it in the chat box. Okay, we'll check it with that. So here we are, first of all, we are moving with artificial magnets. So where we are required of artificial magnets. So we have naturally occurring magnetic material. For them, the magnetic properties are feasible, which means their strength is very low compared to that of artificial magnet. So for using any purpose in real life, we need strong magnets. So that's why we are moving to artificial magnets, and artificial magnets are made up of alloys like alnico, a combination of alloy of aluminium, nickel and cobalt. So artificial magnets are especially made up of alnico. And so what's the need of artificial magnets means? What's the need of artificial magnets means? The naturally occurring magnetic materials have very low strength and we can't directly use them into for any purpose in real life. So that's why we are moving to artificial magnets, and there are different types of artificial magnets, especially bar magnet. So a magnet in the form of a chocolate bar, a magnet in the form of a chocolate bar. So that's what is called a bar magnet. Magnetic needle, you may familiar with compass, not that compass that you are using in geometry in mathematics. It is magnetic compass, those who used by the navigators in ships for directional purpose, and magnetic needle. So in that compass you can see a needle, that is actually a magnet. A artificial magnet is that one. A magnetic needle, that one is a magnet. And horseshoe magnet, you may see with U-shaped magnet, is also known as U-shaped magnet, since it in the form of a U, in the form of U of English alphabet. So it is also known as horseshoe magnet and ring magnet. Ring magnet is there. There are disc magnet. There are different types of magnet. And in this chapter, we will be especially dealing with bar magnets. Okay, so there are different properties that we are dealing with. So especially we will be dealing with in this chapter, especially the bar magnets. Okay, so we can discuss basic, okay, C is missing. Okay, basic properties of magnets. Okay, basic properties of magnet. So you are very much thorough with these basic properties, since we are from your childhood we are dealing with magnets. So you know that like poles repels and unlike poles attract. So like poles means a north and north pole, they will repel each other, and a south and south pole will repel each other, and a north and south pole, unlike poles, they are unlike poles, they'll attract each other. Same kind of property we can see with magnetic charges. So a plus charge, they are like charges, so they will repel each other. A plus charge and minus q charge, these are unlike charges, they will attract each other. So you can see the resemblance with electric charges. In the magnetism, like poles repel each other and unlike poles attract each other. So the same case you can see with electric charges. Same charges repel each other and unlike charges attract. So that's why it's told there are very much resemblance with first chapter. Okay, so like poles repels and unlike poles attract. And directive properties, what is meant by directive property? So once you freely suspend a magnetic material or a bar magnet, as you can see here, so what happens? It will align in the geometrical north-south direction, in which the north pole of this bar magnet will directed towards the geometrical north, and south pole of the bar magnet will align in the direction of geometrical south. So a bar magnet, when or any magnetic material which is suspended freely, will align in the north south direction. Okay, so a bar magnet or any magnetic material which is suspended freely will be aligned in the north south direction because of earth magnetism. Because of earth magnetism. So earth is having a magnet within the uh, earth crust, which is not a magnet. So in the earth crust we can see there is molten iron, and this molten iron is rotating. So in that molten iron there will be free charges. So free charges is moving inside the earth crust, and that motion of charges, the motion of that free charges creating current within the earth crust, and that current is producing earth magnetism. Don't think that there is a fixed bar magnet fixed in the earth crust. It's not like that. There will be molten iron within the earth crust in the inner core, and in that molten iron there are free charges. Means iron is being a conductive material, obviously there will be free charges like electrons, and these electrons are rotating or moving within the earth crust, so that motion of electrons creating a current within the earth crust, and that current is producing magnetism for earth. Okay, so that current is producing magnetism in earth. So I have already told you in the previous classes that whenever there is a magnetic field, that magnetic field is always associated with a current, or current can produce magnetic field. Whenever there is a magnetic field, obviously there will be current. A magnetic field is always associated with a current. Within a bar magnet, I have told you in the previous chapter that if we are taking a bar magnet, it is producing magnetic field, right? So it's due to current. So in this chapter we'll be discussing that how a bar magnet is producing current, or what is the current in that bar magnet. Only current can producing a magnetic field. So whenever there is a magnetic field, obviously there will be current, or magnetic field is always associated with current. Okay, so could you follow? Could you follow what's the point I am saying about? So only mag current can producing magnetic field, or magnetic field is always associated with current. Even with we are taking a bar magnet, so it is producing magnetic field. You are very much thorough with that, right? So it is due to only current. A current in there is a current in bar magnet which is producing magnetic field. Okay, which is producing magnetic field. Okay, then magnetic poles always exist in pair. That's the third point. So that's a very important point. It's a very important point. Okay. So in the case of electric poles, or electric charges, they can exist in isolated state, which means a plus q charge alone can exist. A minus q charge alone can exist. But magnetic charges, which means I will be explained, we are using QM, the letter QM to denote magnetic charge. QM is known as pole strength. So QM means Q subscript M is known as pole strength. So it is known as pole strength, or also known as magnetic charge. Magnetic charge. Okay, so you are very much familiar with electric charge, which is represented by Q, plus Q or minus Q. Plus Q charge stands for positive charge, minus Q stands for negative charge. So here we are dealing with magnetic charge or pole strength, which is denoted by the letter Q. Yeah. So in the case of electric charges, there are plus and minus charges. Here also there are plus QM and there are minus QM. Plus QM stands for north pole of the magnet. Minus QM stands for south pole of the magnet. Did you get it? Q plus QM means magnetic north pole. Plus QM represent pole strength, or also known as magnetic charge. And minus QM stands for south pole or magnetic south pole. Okay, magnetic negative charge or pole strength. Okay, so here we have plus Q and minus Q. So if they are equal and opposite charges separated by certain distance, they are called electric dipole, right? So here plus QM and minus QM, equal and opposite magnetic charge separated by certain distance. So it is maybe treated as magnetic dipole. So I will explain later. There is a topic comes like magnetic dipole. I will explain there. So here magnetic poles always exist in pair, but electric poles can be existed in isolated situation, which means plus Q charge alone can exist, minus Q charge alone can exist, but not in the case of magnets. In the case of magnet, their poles or north, if there is a north pole, obviously there is a pair of south pole. They always exist in pair. Suppose if here I have cut this magnet at the middle, so I'll be got two magnets, right? I'll be got two marks out of which this will be north pole and this is our south pole. So what of this pole? Is this one is south and is this one is north? Did it like that? No, never. Obviously, you know that this will turn into a south pole and this will turn into a north pole. So again a pair, north and south pair. Okay, so that is what magnetic poles always exist in pair, or magnetic monopole do not exist. Magnetic monopole do not exist, or electric monopole exist. Electric monopoles means either plus Q or minus Q. So electric monopoles exist, but magnetic monopole is not. Magnetic monopole does not exist, and this is given by Gauss's law in magnetism. So we have learned Gauss's law in electrostatics. Here in magnetostatics or magnetism, Gauss's law in magnetism says that magnetic monopole does not exist, and for our syllabus, for our scope, this topic was not there. And you may please understand that we have learned in electrostatics or in the first chapter. So by Gauss's law, electric monopoles exist, but here Gauss's law for magnetism says that magnetic monopole does not exist. Or Magnetic poles always exist in pair, which means if there is a north pole, definitely there will be south pole. Okay, north pole alone cannot exist. Or plus QM alone cannot exist. If there is a plus QM means pole strength or magnetic charge plus magnetic charge. Obviously, there will be minus magnetic charge, which is minus QM. Okay, and one more, the unit of the unit of this pole strength is given by SI unit is given by ampere meter. Ampere meter, not ampere meter square. It is ampere meter. The unit of magnetic charge or pole strength is ampere meter. The unit of magnetic charge is ampere meter. Okay, so its SI unit is ampere meter. SI unit, SI unit. SI unit of pole strength is ampere meter, denoted by the letter QM. Okay, denoted by the letter QM. Did you get it? So we have discussed. There are several basic properties of magnet, but we are discussing only three because it's not important for our scope, for our syllabus. Not important. Okay, so here we are discussing the first point, magnetic dipole. So you are very much familiar with electric dipole, in which we are dealing with lots of derivations and lots of equation regarding electric dipole in the first chapter, right? Yes or no? So we have deal with many equations, many derivations with electric dipole. So what is an electric dipole? Anyone is remembering? Please put it. What's the definition for electric dipole? Yes, it is two equal and opposite charges separated by certain distance. So two equal and opposite charges separated by certain distance is called electric dipole, and that distance is called dipole length, electric dipole length, right? So equal and opposite, we can consider two charges. Okay, this is plus QM, sorry, plus Q and minus Q. So equal charges Q and sign is opposite. So equal and opposite charges separated by certain distance, and this is what is called electric dipole. So here also we can see a bar magnet. A bar magnet means, I have already said that this is known as north pole or plus QM. This is our south pole minus QM. Okay, so now this become, the strength will be equal for minus QM and plus QM. The strength will be equal. So equal magnetic charges but opposite, plus QM and minus QM. So this is a magnetic dipole. So as by the definition, two equal and opposite magnetic charges separated by certain distance, which means a bar magnet can be considered as a magnetic dipole. A bar magnet can be considered as a magnetic dipole. So what is the definition for magnetic dipole? Two equal and opposite magnetic charges separated by certain distance. Two equal and opposite magnetic charges plus QM and minus QM, and QM is known as pole strength or magnetic charge. Okay, so equal and opposite strength separated by finite distance, and this distance is known as, represented by the letter 12. So as you can see, I didn't mark the pole strength on the tip of the magnet. I marked that pole at a distance, at a small distance from the tip or from the end of the bar magnet. Why? There is a reason. I will explain once we have a topic related to a solenoid as a bar magnet. Solenoid equivalent to a bar magnet. So in that topic, I will explain why this pole is denoted, not denoted on the tip. It is slightly away from the tip of the magnet or end of the bar magnet. Okay, so this length is known as 12, denoted by the letter 12. So in the electric dipole, we have denoted that letter, sorry, that dipole length by the letter 2a. Here it is 2l. Okay, so that's a standard notation that we are used for. Okay, okay. So an arrangement of two poles of equal and opposite strength plus QM and minus QM separated by finite distance. Could you follow? Very easy, right? Very easy. Yes. Okay, so every bar magnet is a magnetic dipole. Every bar magnet is a dipole, magnetic dipole, or a bar magnet can be considered as a magnetic dipole. So in this chapter, there are topics in your syllabus. If you see, you can see that there are several equations related to dipole, magnetic dipole, which means we consider a bar magnet in that situation. So if a equation asks for what is the electric field to a magnetic dipole, means You can state the equation for electric field due to a bar magnet. Why? An electric magnetic dipole means a bar magnet, or bar magnet can be considered as a magnetic dipole. A bar magnet can be considered as magnetic dipole. Okay. Okay, is that clear? Okay, a current carrying loop behaves as a magnetic dipole. In the previous chapter, we have seen that a current carrying dipole, current carrying loop can be considered as magnetic dipole. Okay, so we have derived the expression for magnetic moment due to current carrying dipole NIA. Do you remember this equation? Do you remember this equation? I hope you are. The previous chapter we have seen that. Okay, so you remember the point. A current carrying loop behaves as a magnetic dipole, or every bar magnet is a magnetic dipole. A bar magnet can be considered as magnetic dipole. Okay, easy. Yes. So these are the preliminary concepts that we need to explain more equation in this chapter. Okay, so here we are going to explain some important terms that is related to magnets. Okay, so that's where the chapter magnetism and matter. Okay, so first one is magnetic field. You have seen electric field in the first chapter. That's why I said there are so many resemblances. So what is the definition for electric field? What is the expression for electric field? The region around an electric charge in which its influence can be felt, or in its influence can be experienced. So here it will be the region around a magnet in which its influence can be felt. The region or space around a magnet in which its influence can be experienced. So what is the meaning of that? Okay, suppose consider a bar magnet. So obviously you know that there's a magnetic field around it. So by the definition, the space around a magnet in which its influence can be felt, that is magnetic field, right? So when I kept metallic material, like for example iron, near to this magnet, definitely it got attracted, right? So that's why because once I bring that iron to the field of this magnet, its so its influence is experienced on that iron. That iron block got an influence of this magnetic field. That's why it is got attracted. So once it is not in its field, it will not got attracted. That's why if I am bringing this iron block a far distance from it, it will be out of its influence. So it can't be attracted. So region around this magnet in which its influence can be experienced. That is what is called. That is what is called the magnetic field. Okay, so similarly, the region around an electric charge in which its influence can be experienced is called electric field. So there are very much resemblance with that. So once you learned the first chapter thoroughly, it will be feeling better to learn this chapter. So that's the tip. Okay. So those who are have clarification or confusion regarding first chapter, please make it that thoroughly. Then you can feel very comfortable to deal with this particular chapter. The half of this chapter will be very easy once you are very much thorough with the first chapter. Okay. So here you know that when we are bringing that iron block, or I am taking an iron nail. So once I am bringing that iron nail away, the force of attraction between them will be get reduced. Why? Because as we are moving away from the magnet, its field got reduced, or the influence of this magnet to that region will be reduced. Why? Because as distance increase, the strength of this field reduced. That's a common thing, you know that, right? So that we can apply also here. Okay, so once we are moving that magnet away, iron material or any magnetic material away from the magnet, the force of attraction will be got reduced, because the influence of this magnet over that material will be got reduced, because the strength of the field reduced as we go away from the magnet. As we are moving towards, the strength of that field got increased. Okay, so near to the magnet, the magnetic field, the strength of that magnetic field will be more. That's a common idea that everybody have, right? Okay, so magnetic field. Next one. Yes, next one is magnetic axis. Magnetic axis. So you are familiar with electric dipole axis or electric dipoles axis. So here also magnetic axis or magnetic dipoles axis. So how can we define? Means it is a line passing through the poles of magnet. It is a line passing through the poles. Okay, you can see. So this is north pole and this is south pole, right? So a line passing through these poles is known as magnetic axis. Okay, a line passing through these poles. Okay, so this is a line passing through. Yes, this is a line passing through magnets poles of the magnet, right? So this lane is known as magnetic axis. So this lane is known as sorry, this lane is known as magnetic axis. A lane passing through the poles of the magnet is called magnetic axis. As you know, it is along the length of the magnet. It is along the length of the magnet. Okay, so for a bar magnet, it is along the length of the magnet. Okay, a lane passing through the poles of a magnet is known as magnetic axis. Clear? I hope that is clear. I hope that is clear. Okay. Then next one is magnetic equator. Magnetic equator. So what is magnetic equator? So we are dealing with electric field. In the first chapter, we have dealt with electric field due to a dipole on an axial point, electric field due to a dipole in an equatorial point. So here also we will be dealing with magnetic field due to a magnetic dipole on an axial point and magnetic field due to a magnetic dipole on an equatorial point. So that's why we are dealing with, first of all, we are making thorough with magnetic axis and then magnetic equator. So it is nothing but a line passing through the center of the magnetic material or magnet and which is perpendicular to the axis. A lane passing through the center. So this is the center of the magnet, right? So being this is North Pole and South Pole, this the dotted line I have represented here is the magnetic axis. I can make an extension over it, right? So this is the magnetic axis. So what is magnetic equator? Magnetic equator. What is magnetic equator? So a line passing through the center. So a line that is passing through the center. So I can make it dotted. Yes. Yes. So now this line is passing through the center of the magnet. This is the center, middle point of the magnet, right? So that line passing through the center as well as this line making an angle 90 degree with the axis of the magnet, then that is what is called equator of the magnet. Okay, so the line passing through the center of the magnet and right angles to the magnetic axis, that is what is called equator. Okay, so any point at this equator, any point at this equator can be known as equatorial point. Any point on this axis is known as axial point. So any point on the magnetic axis is known as axial point. Any point on the equator of a magnet is known as equatorial point. Clear? Clear or not? Clear or not? Okay. Then magnetic length. So as I said just a minute before, magnetic length means it's the distance between pole of a magnet. Okay, so as I said, the pole can be represented not on the tip but a distance slightly away from the tip of the magnet. So this is north pole and this is south pole. This is magnetic north and south pole. Okay, so distance between this pole is known as magnetic length, and as I told you, it is represented by the letter 2L. Okay, so you know that here the geometrical length of the magnet is this one. This is the geometrical length, right? So this is the total length of the magnet, but the magnetic length is slightly less than geometric length. This is geometrical length. This is geometrical length, and here I am saying the magnetic length. Magnetic length is always less than geometrical length. So the entire length of the magnet is known as this geometrical length. And here what I have said is the magnetic length, which is represented by the letter 2L. You can see the case of electric dipole length, the length between the poles, electric poles, that is what is known as electric dipole length. Here it is magnetic length or magnetic dipole length, which is the length between the two poles or two magnetic poles. This is plus QM, right? So this is plus QM, this one. This is minus QM, and distance between this plus QM and minus QM is known as magnetic length, represented by 2L. Okay, I hope this is clear. Okay, so the distance between the poles of a magnet is called magnetic length. It is always slightly less than the geometrical length. There is a reason I will explain once that topic is reached. Okay, so magnetic field lines of force or magnetic field lines. Magnetic field lines or magnetic field lines of force, both are same, nothing difference is there. Both the terms are same only. Okay, why it is called field lines of force means they are representation of that force in which a charge is experiencing a force. They are representation of that kind of line. Okay, so it is a concept of representing magnetic field visually. So they are not really existing lines, they are a concept, they are method of representing magnetic field visually. So magnetic field lines means it is a method of representing magnetic field visually. Okay, so as we have seen electric field lines. So what is electric field lines? For a plus Q charge, for a positive charge, it is a line going radially outward, radially outward. So this is a representation of electric field lines. And for a negative charge, it is a line which is radially inward, right? Radially inward. So we have also seen the electric field lines of a dipole. Okay, I hope you are remembering. So those who are remembering electric field lines of a dipole, please put a thumbs up in the chat box. Let me see. Okay, so this is the representation of electric field lines for a plus charge and for a minus charge. And here we are dealing with magnetic field lines of force or the field lines of a magnetic field or a magnet or a bar magnet. Okay, so yes. So it is the path along which a unit north pole would move if it is free to do so. What is the meaning of that statement? Okay, suppose imagine. So we have this is north pole and this is south pole. Okay, so imagine in unit north pole plus qm, I can call it as plus qm. So we have already seen that plus qm alone cannot exist, but for defining it we can imagine a monomagnetic positive charge, monomagnetic positive charge. Okay, so plus qm, if we are imagine a north pole, unit north pole or plus qm charge. So this, since it is a north pole and this is also a north pole, they will, like charges repel or attract, like charges will repel each other, so there will be force of repulsion, so it will have a tendency to move away from the magnet. On the same side, this plus qm, this plus qm got attracted by the south pole, right? This plus qm got attracted by the south pole. This plus qm got attracted by the south pole, it has a tendency to move towards it, right? Towards it. So once we are drawing the force of attraction, attracting lines, the force of attracting lines towards the south pole, it will be like that. Okay, so it will has tendency to move towards the south pole and moving away from the north pole, so that will be getting a line which is representing magnetic field or magnetic field lines of force. That's why it will experience a force to move away from the north pole and move towards the south. So that's why it is a magnetic field lines of force, magnetic field lines of force. Okay, one second. Okay, sorry. Okay, so here this plus qm charge will move towards the south pole and move away from the north pole, so that once we draw the movement of that particle, movement of this positive charge, we will be getting a line, so it will be like this. So when we plot the movement of that particle or movement of that positive charge, it will be like this, and we can give the direction, so it will be move away from it, it will be moving away from it, so this will be directed like this. Okay, so also in the side opposite we can also mark, it will be moving like, so here also we can mark, right? It will be moving not only, okay, sorry, not only this one, we can mark several points, right? So this will be the, so this is the magnetic field lines of force. Okay, so this is the magnetic field lines of force. Okay, so it is a path along which a unit north pole would move if it is free to do so. As I said, once we bring a unit positive magnetic charge near to the north pole, obviously it will repel and it will be got attracted by the south pole. So if I draw the path along which that free charge is moving, that path is representing magnetic field lines of force. Clear? I hope that is clear. Okay, so this is the basic idea behind magnetic field lines of force. Okay, so it is a path along which a unit positive magnetic charge would move if it is free to do so. Okay, so it is a path along which a unit north pole would move if it is free to do so. In a magnetic field, if a north pole magnetic magnetic north pole is free to do so, then that path of that movement is representing magnetic field lines of force. As I said, it can be also called magnetic field lines. It can be also called magnetic field lines. It is, as I said, it is starting from north pole and ends in south pole. Externally, it is starting from magnetic north pole and ends in south pole. So its direction is from north to south. From north to south. So you can see that in the case of electric dipole plus QM and minus QF minus Q. So you have marked electric field lines like this, right? From plus to minus, from plus charge to minus charge. So here it also from north pole to south pole. From north pole to south pole. Okay, from north pole to south. Okay, so as in the case of, that's why I said there's a very much resemblance with first chapter. Okay, I hope all of you can follow this. Yes. Okay, that properties of magnetic field lines, right? Properties of magnetic fields. Just a second. Just a second. Yes. Okay. Really sorry for the inconvenience. Okay. So we are dealing with properties of magnetic field lines. Properties of magnetic field lines. Okay. Okay. Yes. Okay. Properties. I hope that is audible. So, I hope that is audible. Yes or no? Please audible. Sir. Please give me a thumbs up. Sir, audible, sir? Yes. Is that audible? Let me check. Yeah. Okay. So properties of magnetic field lines. First property, magnetic field lines are closed curves. Magnetic field lines always forms a closed curve. Okay. Magnetic field lines always forms a closed curve. So we have seen that this is north pole and south pole. So as I mentioned, magnetic field lines starting from north to south. So it is not closed. It is starting from end and ends in south. But it's not like that. Within the magnet, these field lines are from south to north. Now it is close, right? So for every point we can mark it like that. So starting from north and ends in south is the external and internal of the internal side of the magnet. It is from south to north pole. It is from south to north pole. Okay, so magnetic field lines are formed closed curve. It is in the external part, it is starting from north to south of the bar magnet or every magnet, and in the internal part of a magnet it is starting from south to north, so that it is become a closed path. A closed curve will be, it will be a closed curve. Okay, I hope that is clear. Okay, so next property, the lines of force never cross each other. So we have seen in the case of electric field lines, they will never cross each other. So here also, for north and south pole, imagine that if two field lines are closing each other. Field lines are closing each other. So what happened? So in the case of electric field lines, we have seen that the tangent to the, if for a bar magnet, imagine that. So this is the magnetic field lines. Okay, so this is north and this is south. So this is the direction. Okay, so at this particular point, at this particular point, what's the direction of magnetic field lines? So on this point, we can draw a tangent. and the tangent gives the direction of magnetic field, or for an electric field the same also. Okay, so tangent to that point, particular point, for this point, this tangent at this point, this tangent gives the direction of magnetic field. So for this closing point or closing point, what happens here, we have to represent two tangents, right? Which means at the point of intersection, or the point of closing, the magnetic field should have two directions, which is not possible. So it will be contradictory with the theory. So that's why no two lines of force will never cross each other. Okay, so if they do so, what happens? The point of intersection, we have to set they have two directions. Why? The tangent to that particular point giving the direction of field lines. So here we have to mark two tangents, which is not at all possible. So only the lines of force never cross each other. If they do so, what happen? We should say that they have two directions at the point of intersection, which is not practically possible. Okay, that's why the tangent to that particular point will give the direction of magnetic field, or else for electric field it is also same. So they will not cross each other. So this kind of representation which is wrong. So how can I mark it? How can I mark it? Yes. No two field lines will not cross each other. Okay. This is South Pole. So field lines will not cross each other. Field lines will not cross each other. Field lines will not cross each other. Okay. Field lines will not cross each other. Okay. So this is the representation of field lines. So I can also mark the direction. So starting from North Pole and it is in South Pole in the external part. Okay. So here they start from and end on the surface of the magnet normally. Normally means angle is 90 degree. So here if you are drawing North Pole and South Pole here. So what happens here? At the point of joining the magnet, this point, the magnetic field lines are joined here, right? So at this point, the direction of magnetic field lines will be, this is the direction at this point. Sorry, you should mark in the opposite direction, right? So as it is directed away from the north. Okay, so this is the direction of, sorry, this is the direction of magnetic field. And here, angle between this direction, the angle between the direction and the magnet is 90 degree. That is the meaning of this statement. Okay, so here this is the direction of joining the magnet, because I can draw a tangent here. This will be having this direction. So at this point, so the angle between the magnet and the direction of magnetic field is 90 degrees. That is why they start from and end on the surface of the magnet. Normally the angle will be 90 degree. Angle will be 90 degree. Okay, so that is not an important point. Anyway, we have discussed the properties. Okay, so next one is important point. The relative closeness of the lines give the measure of the strength of magnetic field. The relative closeness of the field lines gives the measure of strength of the magnet. What does it mean by this statement? Which means a magnetic field can be said to be strong if the representation of that field, which means the field lines should be close to each other. If they are not close to each other, the strength of the magnetic field will be less. So here you can see a red, not red, yellow field lines as well as blue. So imagine that this is the direction. Okay. So if in this yellow representation, you can see the field lines are very much close to each other. So strength is more because the relative closeness is very much high. But here the relative closeness between the field lines is less, so that strength is less. So here strength is more. Strength is more, and here it is strength is less. Why? Here the first diagram, the relative closeness is very much high, so that strength is more. So if two wheel lines are represented, two kinds of magnetic field are represented, in which out of which one is having relative closeness is very more, it will said to be more strength field. And if the relative closeness of a magnetic field line representation is very less, the strength of that particular magnetic field will be less. I hope you got that. Yes. Easy, right? Easy, spacey, 11 cc. Okay. So these are some important points, properties of magnetic fields. Okay. So uniform and non-uniform magnetic field. Okay. So here you can see I have given two kind of representation. Okay, so I didn't give the direction even though. So just imagine that these are the magnetic field lines. You can see in both the representation, all the field lines are parallel. Okay, so which one is uniform field and which one is negative non-uniform field? Comment either yellow one or blue one. Whether yellow one or blue one. Okay, comment it in the chat box. Comment it in the chat box. Okay, so here only this yellow color representation of magnetic field lines giving uniform field. So in the both the situation field lines are parallel, but here it is equidistant. All the field lines are equidistant. So here it is equidistant. Field lines are equidistant so that they are uniform. Equidistant means uniform. Not only equidistant, they are parallel too. So in both the cases they are parallel field, but here it is equidistant, so it is said to be uniform magnetic field. Here it is parallel, but even though it is parallel, it is not equidistant because here there is a distance, here the distance of separation is varied. So they are not equidistant, field lines are not equidistant, so they are non-equidistant lines. Non-equidistant. So it is said to be non-uniform field. Non-uniform. Okay. So non-uniform field. So those lines which is parallel and equidistant are said to be uniform magnetic field, and those representation of magnetic field which is not parallel and non-equidistant or which is not equidistant is said to be non-uniform field. That is clear. I hope that is clear. Okay. Have we move further? Yes. Okay, magnetic dipole moment represented by small letter m. I hope you are remembering electric dipole moment. What is electric dipole moment? The strength of an electric dipole is measured using a quantity called electric dipole moment. Electric dipole moment represented by the letter. What is the letter used to denote electric dipole moment? I hope you are remembering. That's why I told in the beginning. Those who are very much thorough with the first chapter will be feeling comfortable with this chapter. Okay, so the equations are also similar. Somehow it is similar. Okay, there are little bit transformation to be done. Okay, so magnetic dipole moment. So we can recollect the idea of electric dipole moment. Okay, so what is electric dipole? A positive charge and negative charge. Okay, minus q separated by a certain distance called 2a, and its dipole moment p. Dipole moment p. Vector p is given by 2a into q. 2a into q, out of which the 2a represent the vector. Length is a vector. Q. Charge is not a vector. It's a scalar quantity. So here electric dipole moment P is a vector quantity whose direction is from. What is the direction of magnetic dipole moment? Sorry, electric dipole moment. What is it? Since it's a vector, the direction should be there. No. So what is the direction? From positive to negative or along this direction, or whether this direction, negative to positive? What is the direction of electric dipole moment? Comment it. Comment it. Let me check the comment box. Okay. So it is not from positive to negative. This is wrong. The direction of electric dipole moment is from negative to positive. Okay, so there is a reversal here. You may be thinking that it is from positive to negative. It's not like that. The direction of 2a, the length 2a is measured from negative to positive. So that's a convention. So you have to follow that. Okay, so direction of electric dipole moment is from negative to positive, which is a vector given by p. P is equal to 2a into q. Okay, so please hold this expression. Please hold this expression in your mind. Okay, electric dipole moment P is equal to 2a into q. So I will put it in the chat, in the box. Okay, please hold this statement, this equation. P is equal to 2a into q. So here we have magnetic dipole moment, which is represented by the letter m. Okay, so it is a product of its pole strength and magnetic length. So what is, did you remember the expression for pole strength? Sorry, the symbol for pole strength, it is Qm. And product of its magnetic length. What is the letter for magnetic length? It is 2L. It is 2L. Okay, or in vector form, I can write M is equal to, I reverse the order, 2L into Qm, out of which this 2L is the vector quantity. Okay, so you can see we have two equations here. We have two equations here. Okay, M is equal to M is equal to yes, M is equal to 2L into Qm. Okay, so M is equal to 2L into Qm and P is equal to 2A into Q. Okay, so listen here, there's a resemblance, right? This is magnetic length and here it is dipole length. Here it is magnetic charge, here it is electric charge. So that is the difference. So there are very much resemblance for this equation, right? So those who are very much thorough with the first equation will be comfortable with this equation too. Only the symbol is changed. Okay, what about the direction? It's a vector quantity whose direction is from here. It is direction from negative to positive. Here it is from direction is from south to north. The direction is from south to north, not from north to south. It is that measured from south to north, or the magnetic moment of a magnet is having the direction of south pole to north pole. This direction from south to north pole, and whose SI unit, what is SI unit of magnetic moment, magnetic dipole moment? SI unit. So did you remember the SI unit of pole strength that I have said? SI unit of pole strength, it is ampere meter. SI unit of pole strength is ampere meter. What about length? Length having a unit of meter, SI unit of meter. So it should be taking product. So it will be ampere meter square. Okay, so ampere meter square is the SI unit of magnetic dipole moment. So did you remember the SI unit of this one? This is coulomb meter. Why? Because coulomb is a unit of charge and meter is the distance of unit of length. So it is coulomb meter. Here it is ampere meter square. Okay, so unit of magnetic dipole moment is ampere meter square, or one more unit is there, or joules per Tesla. Joules per Tesla. This is one among the unit of magnetic dipole moment. It's a vector quantity and taken as a product of its pole strength into magnetic length. Okay, I hope that is clear. I hope that is clear. Okay, so here magnetic field of a bar magnet at an axial point. So magnetic field of a bar magnet at an axial point, or what is bar magnet? I already said that a bar magnet can be treated as a magnetic dipole. So magnetic field intensity of a dipole along the axis, or a magnetic field intensity of a dipole on an axial point. Okay, so this is the scenario. So we have seen a derivation for electric field of a dipole on an axial point. Okay, so did you remember the expression that you have learned in the first chapter? Okay, so here I have represented the axis of a magnet. So this dotted line represents the axis. So here I am interested to mark the point P. Okay, so here we can mark a point P which is on the axis of a magnetic dipole. So here the happy thing is you no need to derive an expression. Only qualitative treatment is provided within your syllabus. So we will be directly go with the equation. So regarding this same kind of expression we have derived in the first chapter in the case of electric dipole. Intensity of electric field of an electric dipole in an axial point. So same kind of treatment we can go for here, but here we will not go for the derivation. We can directly move into the expression. Okay, so I have marked a point P which is at a distance r from the center, so that this entire distance is 2L, right? Entire distance of the magnet is 2L, and what will be this distance? Entire distance is r, then it will be r minus L. Distance between the magnet, this pole and here. So it is south pole, right? It is south pole, and here it is north pole. Okay, so the distance to the point P from the north pole is r minus L. Okay, I hope that is clear. So the magnetic field at an axial point, so B axial is equal to, so we can directly go for the expression, we can directly move for the expression, so which is given by mu 0 by 4 pi 2m into r square minus L square whole square. So this is the expression. Okay, so mu 0 by 4 pi 2m divided by r square minus L square. This is the expression for magnetic field of a bar magnet at an axial point. So as I told, No need to go for the derivation. We can directly write the equation. Okay. So if we are considering a short bar magnet, so short bar magnet means L will be very much less than R. So we are considering a point P which is far away from the magnet, and as well as the length of the magnet is very less, or we are considering a short magnet, so that L will be very much less than R. So this equation can be rewritten as B axial. So B axial is equal to mu 0 by 4 pi. There is no change in that. Mu 0 by 4 pi 2m 2m. So here is this R is missing here. Okay, 2m R 2m R divided by R square minus L square. R square minus L square. Here it is, which implies R square minus L square, which can be approximately taken as R square. So it will be equal to R square whole square, which is equal to R raised to R raised to 4. So this R raised to 4 and R cancel each other. So that what we will be getting is R Q. So this is the expression. So this is the expression for magnetic field of a bar magnet or a dipole at an axial point. So if you see means we can see the same expression for electric field due to a dipole on an axial point, or E axial is equal to, here that constant is 1 by 4 pi epsilon 0. So for a short dipole, and we are considering a point far away from the electric dipole, for same concept, if L is far away from, sorry, A is very much less than R, so we will getting an expression 2p divided by R raised to 3. So this expression we have derived in the first chapter related to electric field due to a dipole on an axial point. So you can see very much resemblance here. The constant is 1 by 4 pi epsilon 0. Here the constant is mu 0 by 4 pi. And here this 2p by R cube. Here instead of p, here we have magnetic dipole moment, just 2m by R cube. So similar expression, right? So similar expression. So those who are thorough with this expression will be feeling comfortable for this one too. Okay, clear? Okay, so next one, a magnetic field of a bar magnet at an equatorial point. Okay, so magnetic field of a bar magnet at an equatorial point. So equatorial point means this, here I have marked the equator of the bar magnet. Okay, so here consider a point P here. Consider a point P. But mark with yellow color, right? Okay, so consider a point P. So in the case of electric dipole, we have derived this expression: electric field of a electric dipole at an equatorial point. So what we have done there is, we are considering a point charge, unity positive charge or unity point charge, and we are dealing with the force of attraction or force of repulsion experienced by that point charge due to the positive and negative electric charges. Here also we can go, similarly we can go for deriving expression for magnetic field of a bar magnet in the same way, but here the derivation is not at all required. Here we can directly write this expression. So in this case, so if we are going to derive this expression here, so what we can do is, we can consider unit positive magnetic charge or plus qm. So here we can consider plus qm charge at the point P. So since it is a positive charge, it is north pole and this is south pole. No, so this is north pole and south pole. So since it is a positive charge, this north pole will repel that charge. So if the charge is here, since it is a repulsion, the force of repulsion will be, I'll mark it here. Okay, the force of repulsion will be like this, and since it is a positive charge, the south pole will attract this. So this will be attracted towards it. So I can mark it. Okay, so there will be a force due to the north pole, there will be force due to the south pole, and due to this force, since they are vector quantity, the resultant will be in midway between that. So this is the resultant force for that positive charge. Okay, so this is the method that you have followed to derive the expression for electric field due to a electric dipole at an equatorial point. So same method we can adapt it here, but derivation is not at all required. We can directly move into the expression. Okay, so why I have explained these things, because to get the expression for this magnetic field at an equatorial point. So in the case of electric dipole, we have got the direction from positive to negative or towards left. Here also, since the force direction is towards left or north to south direction, it will be also having here. This is the direction of magnetic moment, right? From south to north. So it is having, this force is having just opposite direction of magnetic moment, just opposite direction of magnetic moment. Here also, this magnetic field at an equatorial point will having the opposite direction of magnetic moment. Okay, that's why I have explained this diagram. Okay, so we can directly write this. We can directly write the expression as. We can directly write the expression as B. Sorry, B equatorial is equal to, again the constant here is mu 0 by 4 pi, mu 0 by 4 pi m divided by, the previous case it is 2mr, here it is only m divided by r square minus l square, r square not minus, r square plus l square all raised to 3 by 2. So this is the expression, r square plus l square all raised to 3 by 2. Okay, so this r means this length. Okay, so r is this length, length from the center. Okay, so l means this length. Okay, so this again is, if we can go with the same approximation, which means L is very much less than R, which means the length of the magnet is very short and we are considering an equatorial point which is far away from the magnet, so that L will be very much less than R, or which implies we can take this approximation, R square plus L square can be approximated into R square. So R square all raised to 3 by 2, I can write it as R cube. R square all raised to 3 by 2, I can write the expression as R cube. So this equation becomes B equatorial is equal to mu 0 by 4 pi. There is no change in that. Mu 0 by 4 pi m divided by R cube. Okay, this is having a negative sign because, as I told here, m is having direction from south to north pole, but here this force is having the opposite direction of m. So which means the magnetic field at an equatorial point having a direction just opposite to the direction of magnetic dipole moment. That is why there is a negative sign. So this is the expression for. So this is the expression for magnetic field of a magnetic dipole at an equatorial point. Okay, so there is a resemblance. There is a resemblance with the electric field in the first chapter. Okay, so did you remember that expression? Okay, I will write it here. Okay, I will write it here. Okay, for an electric dipole at equatorial point, electric field at equatorial point is given by constant. There is 1 by 4 pi epsilon 0. And there is magnetic dipole, not electric dipole moment is there. Here it is magnetic dipole moment. Dipole moment is having direction P divided by R cube. It is having negative sign. So this is the expression for electric field that we have learned in the first chapter for an equatorial point. Here there is an expression for magnetic field for a magnetic dipole at an equatorial point. Okay, you can see the resemblance. Constant here and a constant here, the electrostatic, constant here in the magnetostatics. Here is the magnetic dipole moment, here it is electric dipole moment, and R cube. Okay, so that's why I told there is a very much resemblance. So those who are remembering this equation will be comfortable for this equation too. Okay, so we can move to the last topic of today's class, which is torque on a magnetic dipole in a magnetic field. Okay, torque on a magnetic dipole in a magnetic field. We will not dealing with the derivation, but there is 1 or 3 steps is there, so that we can derive that expression too. Okay, only equation is needed. Okay, so here I have considered electric magnetic dipole, which means a bar magnet. A bar magnet can be considered as a magnetic dipole. Okay, so I'll mark. So consider a magnetic field, uniform magnetic field. Okay, so having this direction, which means this is the direction, means this will be the north pole and this will be the south pole, right? So here it is, since it is a south pole and this is magnetic north pole. Okay, so we know that there will be force of attraction towards south pole. A south pole will attract north pole, right? So there will be a force of attraction. This is F, force on north pole. and since this is south pole and here it is a north pole, it will be got attracted here. Okay, so this is force of south. Okay, so we have seen the expression for force experienced by a charge q placed in an electric field E, F is equal to QE. So did you remember this equation? Force for a charge Q placed in an electric field, F is given by F is equal to QE. Similarly, we can have the expression for force experienced by a magnetic charge QM placed in a magnetic field B is equal to QMB. Similar expression. This is F is equal to QE. This is F equal to magnetic charge into magnetic field QMB. So this is the force here. This will be the force here. Okay. So here Fn and Fs have equal magnitude since it is a uniform magnetic field and the pole strength are equal, right? This pole strength and magnetic fields are equal. So Fn and Fs have same strength but in opposite direction. So did they cancel each other? Did they cancel each other? No, they will not cancel each other because they are not collinear. Only collinear force can cancel each other. Here, these forces are in the opposite direction. One towards right and one towards left. They are not collinear. They are acting in different lane. So they will form a couple. What is coupled of force? Two equal and opposite forces and their line of actions are different. That kind of forms are known as, that kind of forces or that kind of vectors are known as couple vectors, or here it is force, so it is couple of force, a couple of force. So they are equal and opposite. And when there is a couple of force, it will not cancel each other and it will give rise to a torque. Here it will give rise to a torque, and expression that for that torque is given by F. Torque is equal to tau is equal to force into perpendicular distance. Force into perpendicular distance. Okay, so here the force is, what is the force here? Force is this one, QM into B, QM into B, QM into B. So what is perpendicular distance? Perpendicular distance means this distance between, the perpendicular distance between these force. So this is the distance, sorry. So I need this distance, perpendicular distance between this force, which means here there is our first force and here the line of action of second force. So I need this distance. This distance should be measured. So we have this magnetic length is equal to 2L. I already told you that expression derivation is not at all required, but anyhow I am explaining. Only 2 or 3 steps are there. That's why I am explaining. So here, if this angle is theta, this angle is also theta. So from this expression, and if I need this length, once I go take the sine of this right angle triangle, I will get this length as, once I take the sine, this length will be equal to, if it is AB, if this length is AB, then I got the expression AB is equal to 2L sine theta. You can take the sine of that particular angle, so that it will be equal to opposite side by hypotenuse. Hypotenuse is 2L. So that if I take the sine, then AB will be given as 2L sine theta. Okay, make a rearrangement, you will be getting that expression. So now here this length is, length between the line of action of force, this length is getting as 2L sine theta. Okay, so I can substitute here. Perpendicular distance is 2L sine theta. So 2L sine theta. 2L sine theta. Okay, so I again rewrite this expression as QM into 2L into B. Okay, sorry. Okay, 2L into B sine theta. So what is Q into 2L or 2L into Q? What is 2 into QL? 2 into QL, 2L into Q, which is equal to magnetic dipole moment, right? So I can substitute it here. You can substitute here, which is equal to MB sin theta. MB sin theta. Okay, so torque is equal to MB sin theta, or in vector form, vector tau is equal to M cross B. Vector tau is equal to M cross B. This is the expression for torque experienced by a magnetic dipole placed in a uniform magnetic field. Okay, so this is the expression for torque experienced by a magnetic dipole placed in a uniform magnetic field. So we can see, remember this equation, torque experienced by an electric dipole placed in an electric uniform magnetic field, which is given by P cross E. So you can see this expression in the first chapter. Torque experienced by an electric dipole placed in an electric field, not magnetic field, placed in an electric field. So that's electric field. When a electric dipole is placed in an electric field, this is the expression for torque. Torque is equal to P cross E. P is the electric dipole moment, is the electric field. Here it is a torque experienced by an electric dipole placed in a magnetic field. It is, sorry, vector symbol is not given, right? So this is equal to, torque is equal to M cross B. M cross B. So you can see the resemblance. You can see the resemblance. Okay. So this is why I told you that there are very much resemblance for the first chapter and this particular chapter. Okay. So we have seen every expression, there is a relation in the first chapter. So those who are, I am again repeating that those who are very much thorough with the first chapter will be comfortable with any equations in this chapter. So there is no derivation comes in this chapter, only qualitative treatment is needed. That's why we have directly gone to the equation, and that's why I didn't explain a lot for this particular diagram. I didn't explain a lot, only this equation is needed. Okay, so those who are compare and study will be feeling comfortable. Okay, so that's all of for today class. Okay, so any didn't have any those who are having any doubts, please put in the chat box. I will explain it again. Okay, or else on 25th of October, this coming Saturday, sorry, coming Wednesday, our Amala ma'am from Department of Biology Goscore Learning will come with the 5th chapter of grade 12, Molecular Basis of Inheritance, and part 1 video of the particular chapter. So please stay tuned and happy learning for all. Happy learning for all. Thank you.